Right. Okay. Well, where did I get to? Yeah. I'm using a pair of Yagis. So it's a small system, small aperture system. So I get very weak signals. And the work I've been doing is to, at the moment, to develop this software so that I can analyze the data in a reasonable sort of time. There are already some there's already some pulsar software that amateurs use. Probably the pioneer is Andrea Dell'Immagine and his son Giorgio Dell'Immagine. He's in Italy and he's developed some software which most amateurs use now, to be perfectly honest. It's his own Linux application that he's developed, and it outputs data suitable for Presto. Presto is one of the professional software, and he's produced some very good results. Marcus, who we've heard before, he's also produced a package, a GNU radio package, and he's been using that very successfully. Michael Klaassen from Holland has also produced a little software package, and he calls it 3PT. It's available on his website here, and this is a Windows application running in Python, and he's produced a very neat graphical user interface as well. Both Andrea's and Marcus's software produce data in filter bank format, which is suitable for most of the professional packages. And Presto is an excellent package. The problem that I find is that it's really been designed for professional applications, actually to find new pulsars, not to analyze them. And it really needs quite a strong signal. You do need a decent size aperture to be able to use it. With my system, typically the sort of signal to noise ratios that I do find on a successful day are about between 4 and 7 to 1, and Presto isn't quite as good as that. But the software that I've looked at developing aims, that's my target to aim for, to produce a sort of presentation from which you can just look at it and say, well, yep, that's a valid pulsar that I've got. I've put these links up. If you don't, they're not in the conference paper, but I have submitted an article for the April journal, and these links are in that. So first of all, if you're going to identify a pulse, you really need to understand its properties, and I've listed the main ones here. Basically, you receive them as a sort of regular pulse train. That by regular, I mean that it's a nominal pulse width, but it's a very accurate, predictable period. Wolfgang said they're accurate to 10 to the minus 15 parts per minute, accurate to 10 to the minus 15. So they're a very highly stable source. They've got a predictable period, and P dot is its period rate. This is the rate of change of period, which is one of the tests. You shouldn't be able to measure any change in period, not over the typical observation times. They're a very wideband noise source. They're dispersed in frequency. The lower frequencies arrive after the higher frequencies. They scintillate, and they scintillate in time. Their amplitude varies from pulse to pulse and from frequency to frequency. And when you're measuring them, if you're measuring in drift scan mode, as I usually do, then the amplitude of the pulse, the data you receive, should follow the beam pattern. So this is my system. It's a pair of Yagis, 2.5 meters long, tuned to the 611 megahertz radio astronomy band. So they're 2 homemade Yagis. They've got low noise amplifiers directly at the reception point. They both feed into a box, into a sort of lossless combiner. It's got a loss of about 0.1 of a dB. Then it feeds, then it feeds into an amplifier, and then it goes into my garage here. And this is the receiver. So the RF comes in here. It goes through another low noise amplifier, a filter, and then back through another low noise amplifier, and then into an AirSpy SDR. There's a GPS disciplined oscillator that that locks the AirSpy. It's quite important when you have a weak signal that you do know that you tune that the clock frequency is very accurate, and the GPS DO locks the clock frequency to 10 megahertz. This all goes into an aluminium box that I've shown here. This is that receiver panel that's here. There's a traditional type power supply, no switching power supplies here. And the power supply is disciplined by a 12-volt battery. And the AirSpy links to the PC via a USB link. This pushes in and the lid closes down in operation. So the data collection and pre-processing, I've copied Marcus Leach's, he calls it a stupid, simple pulsar program. It's not stupid and it's not simple. But I've used the cut down version of his program, and that actually drives the AirSpy.
And just to fool the enemy, Peter.
Just to fool the enemy. What the stupid side, it's certainly not stupid. And then what the GNU radio does is it splits it up, the frequency, into a 16 channel FFT. It does power detection and decimation and integration. And this effectively cuts the data rate down by a factor of 1,250 in my case, and outputs a 32-bit binary file. So it's 16 channels, and I've chosen to use a 2 millisecond clock. This is the GNU radio flowchart, which I stole from Marcus. There's the Osmicon source box, which controls the AirSpy, and that feeds into this head unit, which controls the number of samples that the receiver takes. And here it's 168 gigasamples of INQ. It turns that data into 16-bit blocks to feed into the 16-point FFT. The output, the 16 outputs are then converted into magnitude, into power, and then I use an integration block to divide this, to decimate it by the factor of 1,250. And then that data is collected. And basically in this case, the 168 gigs is a an observation time of about 4 hours and 40 minutes. And in that time, the pulsar crosses the beam of my pattern. The post-processing functions, this is the bit that I've done. What I do is I take these 16 and they're 8.4 megacycle files at a 2 millisecond clock, and I compress the data, and I also do a match filtering process on it to reduce the data down to 16 by 131 kilosamples, now at a 0.7 millisecond clock. And I'll explain the compression and the match filtering in a moment. Now, you might be asking, how can you get 0.7 millisecond resolution when 2 milliseconds is going in? But you've got to realize that this data is clocked with a clock of 1 part in a bit accurate to 1 part in a billion. And so all the timing is there, and providing you've got enough pulses to so that they do stack up here, then you can improve the resolution into even better than that. After that, I remove the DC offset because whatever happens, there is the temperature changes, and so the baseline can change in the data collection process. So you remove the DC offset. I in fact calculate the mean and standard deviation, and that's for looking at later. I've got the facility in it to do video RFI blanking, so I can blank some of those FFT channels, or I can blank some of the blank them in time. And then I fold the data down into 16, fold the data into these into this lower data rate. And then on the right hand side, I've taken the data from this box, and there's a test mode where I can do a period match. When you do your folding, it's the clocks may not be right. You need to know the exact period that you are receiving the pulsar at, and that depends upon the time of day and your location. But there's a program called Tempo, which is very easy to use, and that can tell you the current exact whatever UTC you're doing your observation at, and for your site it can tell you exactly what the what period you can expect. Although the pulsar period itself is highly stable, the Earth is moving around the solar system, and so there is a Doppler shift to the signal that you receive, so that has to be adjusted. So there's a test mode that so that you can set the period up for your doing your synchronous detection, or folding as we call it. And then we can do a band search and a dispersion measure search, and then once that's done we can look for best profile, and there's another number of other programs that we can do. And in fact, the program that I've developed to do all of this function produces about 21 files of all of this, containing all of this data, so that you can look at it and expand it and see how it's getting on. But now I'm going to look at how to compress the data and still maintain it. I'm using a technique called partial folding. Now, normally you take the data that you have, you chop it up into exact period blocks. And then normally what you do is that you stack all those period blocks on top of one another, and that's called the folding process. The because they're precisely the period, when you add them all up, the pulsar will always be in the same place. So that adds linearly, the noise adds as the power, and so the pulse increases as the square root of the number of sections. But what I do in partial folding is that I chop the data up into a number of blocks. And in my case, I've chopped it up into 128 synchronous blocks. And I fold each of the blocks separately, like this, and fold them all separately. And then, so I've effectively divided this data rate by the number of sections, which in this case is 128. So I've compressed the data by 128. And the way it's compressed is that I add all of these single pulses together. So I get 128. It's effectively 128 periods because they've each got a pulse in. And I can add those together, and they give me precisely what would happen if I added them all together. So in fact, what I've achieved is that originally 23,500 pulses, I've reduced to 128. So I've divided the data rate enormously. And I do all my processing on this compressed data. And because it's only 128 samples long, periods long, then I can do a lot of software and do a lot of, and I can do a lot of these processes, and they can happen very, very fast. The next thing is matched filter folding. If we look at this one here, this is data that I've used from the Vela Pulsar, which Guillermo Gancio from Argentina gave me. If you take the data normally and you fold it, then the ideal number of bins to fold the data into is the ratio of the period divided by the pulse width. And for Vela, that is 40. And if you use 80 bins, then the signal to noise ratio goes down. And so this green line is the theoretical curve. If you just folded the data raw, and this is the number of bins. And the red plot is folding from about 10 bins to about 800 bins. And you can see that there's a lot of spread here, but it gets very close to the to the theoretical. But what the folding process is doing is it's averaging the data, and averaging is the same as filtering. So instead of using the averaging process to do the filtering, you can do a match filter. And in this case, you get an optimum, this magenta line, that you get an optimum signal to noise ratio, regardless of the number of folding bins. And the way you can match filter fold is by, if you're used to using the spectrum, is you take the spectrum of the data, take the spectrum of the pulse shape, and here I've used the Gaussian pulse shape, the same as the same pulse width as the Vela Pulsar, which is about 2.7 milliseconds. And if you multiply those two together and take the inverse FFT, then that's equivalent to doing the filtering process. Or alternatively, you can FFT the data and filter the high frequencies. Or alternatively, you can build yourself an analog filter or a digital filter. But I find once you've digitized the data, it's very easy to use the Fourier transform to do it. On the right-hand side is the same thing, but now using the BO329 pulsar, which is the one that is the strongest pulsar in the Northern Hemisphere. Once again, this is a very high signal to noise ratio. We're looking at about 50:1 signal to noise ratio. For the BO329, the signal to noise ratio is just over 4:1. And you can see with filtering, there's a much wider spread, which you can expect because of the lower signal to noise ratio. But if you try to, the red dots is doing a fold with using just the number of bins to do the averaging. And you can see there's a slight improvement here as you get down to this low level. You are getting some peaks here, but here it's just running on the normal noise level. So that's just noise. You can't see much of a pulse. It's not, although a lot of people do use 108 bins for BO329, because the bins are effectively the pulse width wide, then you get a very wide variation in practice because the pulse could spread over 2 bins. Ideally, you'd like it to be right in the center of a bin, but you've got no control over where the pulse lies phase within the bin. So with the compression and the match filter folding, I get a very short pulse, a very small file, which has got all of the information that it would have whatever method you used. Incidentally, the folding algorithm can't be beaten. Whatever you do, if you match filter it, the signal to noise ratio you get will be the best possible. I haven't found a better algorithm for pulling pulsars out of noise. So this is the program. It's called SynCompressX. This is the data file. It's calling up 16 channels. 2 milliseconds is the data clock. 714.492 is the topper centric period. 128 sections. I've got 1,024 bins. The nominal pulse width is 6.5 milliseconds. 26.7 is its dispersion measure. 0 is, this is where you put in any possible period adjustment in parts per million. The 04 calls up, actually controls the period search range. You change the O into a T to go into test mode. 10 is the RF bandwidth, 10 megahertz. 611 is the RF center frequency, and 32 is a rolling average number, which I'll tell you about later. Now, if you run this program with the 4 hours and 40 minutes of data that's already been decimated by GNU Radio, the program immediately prints out this data, which is factory calculations from this, and then it produces and it runs and produces 21 files, which I'll tell you about in a while. This is the test mode with period adjust. If you put a T in where that 0 was, then it prints out what the signal to noise ratio is as you change the period in parts per million. And you can see here you get the maximum of 4.85 at 0, and P dot is the period rate change, and you can see that they're both 0. So there was no adjustment needed here. To run the test mode, that takes 10 seconds. To get the full output test file, it takes 25 seconds, and it produces all this data. The raw compressed channelized data, the compressed filtered channelized data, compressed filtered and combined bands, that's all the bands combined together. The pulse profile, it does a period search, a period rate search, a 2D period search, a number of dispersion measure searches, band peak, and it does the bands. These are various band folds. And then it looks at the sections, looks at the cumulative sections, and then it does these rolling average sections, which I'll tell you about. So all of those files, actually, most of them do folding operations. There's no data manipulation at all, although you can input data in two files. I call them blank sections and blank frequencies, where you can blank out sections and frequency bands. So now let's look at some data. This is the pulse profile. You'll see there are two profiles here. There's a blue one and a red one. The blue one is in fact the best signal to noise ratio, using all of the data at the optimum dispersion measure point. But the red one is even higher than that, and I'll explain the reason for that later. So this is the period P dot search files. The period search is in red and the P dot search is in blue. I'm only going over a range of about plus or minus 4.5 parts per million. The P dot search is over a similar sort of range, but there are parts per 10 to the 10. And with them both peaking up at 0, tells us that the period is what you expect from tempo, and there's no period change during this 4 hours 40-minute period. And we're looking at parts in 10 to the 10 there. The next process is the period P dot search, and this is where you vary the period and you vary the period rate both together. And you see you can get an extended spot here. What you expect to see is a peak at 0, but here you can see that there's a line. Now what in fact you do get is a ridge, because if you vary the period and do a fold and vary the P dot in the opposite direction, the P dot kind of compensates for the offset that you've done on period, and so you get a ridge. And what I've done here is that we know that that ridge slope is dependent upon the number of pulses in your observation, and twice the period rate change, twice the period change divided by the period rate change is dependent upon the number. And so I've set these scales so that that comes at 45 degrees. So it's very easy to see. And in fact, of the 25 seconds of those 25 files being produced, this takes 10 seconds because there's 2,500 combinations, because it's a two-dimensional. For dispersion search, what we do is I've got these 16 bands here. I've shown just 3 bands, and I do it relative to the center band. and because it's all digital, I can advance or delay these and then add them up and then look at the data sum. And this is doing a dispersion measure search, because what I'm effectively doing is varying the rate of the dispersion across here, and I can vary it either positively or negatively. And ideally, when the low band delay is compensated for the interstellar delay, then you should get a maximum. And this is our dispersion search. Here we can see this is the data as we see it. As we get near 26.7, it peaks up and then it rolls down. And the problem that we've got here is that, as you saw on those period search plots, it's quite a low signal to noise ratio, and so the base noise is affecting the quality here. So what I've done here is that I can patch out. I know where the pulse is, and so I can patch out where that pulse is. I can blank it and do another search, and then I get this line here. And if I subtract the two, then I get just I get this blue line, which is just the part that the chosen pulse is doing. So we're looking at it, and you can see that it's kind of moving over closer to this point. But it's clearly showing that the dispersion, that it is a dispersed signal, and it is close to where we're looking at. This line along here is the bin number that it appears, and there's no change in this period. That's where we get the bin number from, that I can patch it out. With the frequency channels, the green dotted line is the signal to noise ratio of the peak of any noise, peak or signal or noise in each of the bands. The blue dotted line is the signal to noise ratio of the target pulsar, and this is the target pulsar's bin number. And what I've done here is that each one of these, so I'm folding band 0, folding band 1, folding band 2, and looking at the peaks to get these values. Now with a cumulative fold, I fold band 0, and then I add it to band 1, and I fold band 1 and band 0. And then I add bands 0, 1 and 2 and fold those together and get this value. And then I carry on doing that until I've folded all the bands together. And you can see that the green is the noise peak, and the target signal takes over at about band 3, and it climbs up. And this steady climb is what you'd like to see from a cumulative fold. So that's showing quite clearly that there is a signal of varying levels, showing that it's scintillated in each band, but the signal is integrating over all of the bands. Another way of showing that the cumulative band is to show all of the bins as you accumulate the bands, and you can see that the noise gives us these green striations, but once again the target signal rises out in blue to integrate to that. Normally in Presto they do this with section numbers, discrete section numbers, but I've done the cumulative sections here, and they similarly add up. And here you can see that the signal starts rising up by about section 40 of their 128 sections. This is another plot of this is the number of sections, 128 sections. And here I've accumulated the signal. So we're adding up, this is the accumulated fold of 20 sections, 40 sections, 60 sections, 80 sections, and so on. And you can see that once again, the signal is integrating out of noise to give us our peak. What the green and the blue are is the noise. So here I've just selected the target to give me the red line. But the blue is from, I think the target bin number is 637. So the blue is 0 to 630. And you can see that the noise just gives us a sort of level. And the green is from 640 to 1023. So you can see that there's no other noise peak that is exhibiting a steady rise. But the other thing that you can see is that there are regions of very fast rise and some regions of falls. And this is where it's probably a preliminary indication of scintillation. So in this region, we've got a strong signal. In here, we've got a weak signal, or it's being subsumed into noise. So this is scintillation directly. This top plot is BO329 taken with a 46-meter dish, which shows us pulse by pulse what the data is. I think I can do this, yeah. If we look at my data, my equivalent data, no, I can't do it. No, it won't let me do it. Yeah, my equivalent data for the 128 sections by 1,024 points is just noise. You can't see any pulses there at all. But because it's digital and I know the bin number that the pulse is arriving in, I can select that bin number, and that's what I've done here. So, and what you can see is that there is evidence of scintillation just by looking at those bin numbers. There's some negative ones, it's all largely positive, and that's another indication that you've got a signal that's integrating. There's another clearer method of doing this, and that is to do, I've said that we accumulate them, but you can do a rolling average. And what a rolling average is done, what this is 32 sections. So I've taken section 16 and I've taken 16 sections below it and 16 sections above it, and I've averaged those, I've added them together, I've folded them, and I've produced this point. And I've done that for every point along here. And you can see that there is that these 32 sections, as I move along here, there's a point here where about 48, 49, where the peak signal to noise ratio is bigger than anything that we've measured here. And this is the one that's responsible for that red plot in the profile. So what it's saying is just 32 sections around here gives me a better signal to noise ratio than the whole lot. The other thing it does do is it shows that this scintillation, where we're getting these areas where we're getting strong pulses, because this is all the particular one. But more importantly, it also shows my drift scan antenna pattern. So that's another confirmation that I'm really looking at an extraterrestrial source, because I'm pointed at the sky. So I've done 32 sections and shown that we've got a pretty good signal to noise ratio. But what I can do is that I can do a rolling fold of 2 sections, 3 sections, 4 sections, 5 sections, 20 sections, 40 sections, and so on. I can do a rolling section of all of these, and I can find that at this point here, which is section 96, that I've got a very high peak signal to noise ratio. So that means that if I center it on section 51 and just use the 48 sections either side of that, 96 sections, then I can get a better result than folding all of the data. So these techniques that I've just explained enable you to actually study the observation that you've taken to convince yourself that it really is a pulsar. All of these things all link together and give you a consistent output. And you can plot all the output, and this is similar to what Presto does. And if you saw Presto results like this, then you would say that is definitely a pulsar. But here we're looking at a pulsar at an observation that appears to be only about 5 to 1. Remember, initially when I did the original period search, it was 4.85 to 1. So in winding up, I've told you about an alternative GNU radio compatible software. It includes fast processing for evaluating low signal to noise ratio pulsars. It collects, compresses, and improves resolution. It allows RFI mitigation and pulsar validation. It gives you a range of analysis files to explore pulsar detail. I haven't gone into everything today. I've told you most of it. Cumulative signal to noise ratio for time and frequency analysis is a good thing to do, and rolling averages, I'm really pleased with the results that I get for that, because it can spot both scintillation and antenna pattern modulation. Advantage of GNU radio I haven't mentioned is that it can work on a range of SDRs. I've used AirSpy. It will run RTL and HackRF and anything. So there you are. Okay, so that's my talk. I hope I've managed to keep you
Thank you,
interested.
Peter.
Okay.
Thanks very much. I see Rich has a question about looking for an FRB.
Well, their single pulses. This really, the advantage, the reason I can use my software is because I've recorded 23,500 pulses. So that's why I'm able to compress it the way I do. For single pulse FRBs, I'm afraid you've got to go to Presto.
I've got a couple of questions, if I could, real quickly.
Yeah.
What do you think your timing source might be adding to some error here and giving you that, giving you more of a diagonal in that spread than you would have otherwise if you had a more accurate timing source?
Well, I use a GPS disciplined oscillator, which is accurate to 1 part in a billion.
But the pulsar is more accurate than that. So
yeah. Oh yes, yeah. Well, that's the reason why I didn't see any variation in the P dot. The width of this is really due to this effect.
Yeah, that's where I think you might have some timing error. That it might not be such a long diagonal if it was more accurate.
Oh yes, the diagonal will almost full length. What I did in the paper that I've submitted for the journal, which covers a lot more than what I've spoken about today, there is a very detailed explanation for this plot, and that is doing exactly what I expect it to do.
Okay.
There it is spread a bit more, but that is due to the underlying pulses.
And I wondered if you looked at adding, have you looked at adding a couple more antennas and looking at polarization?
Yeah, I did. Right at I can look at polarization. My antenna, I built it so that I can turn them round by 90 degrees, and I have tried horizontal polarization, vertical polarization, one way, one the other way, and I get similar results whatever I do. But I haven't tried doing pulse analysis. My research has really been to find out how low a signal to noise ratio measurement I can recognize.
At the frequency you're at, you don't see atmospheric changes in polarization that
No,
might be.
Actually, if you looked at my data, the quality of it is very high. The reason it's high is that I took this data last October, and where I am in October, those measurements were taken about from about 12:30 in the morning to about 4:30. So it was right in the night time where everybody's asleep, nobody's using washing machines, no one's mowing their lawns, nobody's doing any DIY, nobody's running their computers, they switched them all off. And I had virtually no RFI in that measurement.
Actually, Peter, I have a question in that regard. The radio astronomy band, which is notionally NTSC channel 37, I thought that was reserved for radio astronomy only in ITU region 2, which does not include the UK. So does the UK have their own reservation for radio astronomy in that band?
Yeah, yes, yeah.
Oh,
yeah.
okay.
Yeah, 608 to 614.
Yeah, 614. That's NTSC channel 37.
Yeah,
which
at 615, 616, we've got TV stations, but the filters I use are very sharp.
Did I send you some filters? I don't remember.
No, you didn't. I did ask one time.
Yeah, because I have some filters that I had custom made for that frequency range. And I just don't. I do know I sent one filter to somebody, and I couldn't remember whether it was you or somebody else.
No, I got mine from Czechoslovakia actually, but I have built my own. I think it's best to build. The one I built was 6 megs wide for my triple RTL receiver, but when I went to AirSpy, I found that I could use a pair of these Czechoslovakian filters, and they did the job. And because it was at night, I did try to do some measurements during the day back in July, and that wasn't fun at all. I was just dashed with RFI.
Well, I do know that BO329, or I recall that its polarization does rotate over time. So your best approach is to use a dual polarization reception setup, and then do, post detection combining of some sort, and that'll give you, effectively you get scintillation and polarization showing up. So if you happen to have a dual polarization receiving setup, you can still see it even when it's rotated away from one of the polarizations.
Yeah, I think the polarization rotates during the pulse.
Yes, I think that's atmospheric effects on the signal coming through the atmosphere,
Is it?
not RFI, that can rotate your polarization.
Well, I don't think atmosphere is going to rotate the polarization at that frequency. Ionosphere maybe, but again, at 611 megahertz, I wouldn't expect there to be that much rotation going on. I thought it was inherent in the pulsar emission mechanism, or it's part of ISM scintillation, that the polarization effects show up. But it's been a while since I looked at it, so I don't remember.
When Wolfgang was confusing his polarization, he saw polarization through rotating during his transit. I have a question, if I may.
Yep.
RFI, what is your technique for the RFI blank you had on an early slot? Is it take the neighbor and just copy it, or is it take the average of its neighbors, or
That is just,
what's your method?
It's just a blanker channel. So I've got 128 sections, and I can blank any of those. And I've got 16 bands, and I can blank any of those.
So by blanking, you just ignore it and don't use it?
Just ignore it and don't use it, yeah.
As opposed to putting a magic disabling number in there.
Yeah, yeah, I can just blank them. There are two, the software calls up, looks for two blank files, and they just have numbers in them, the number of the section to blank and the number of the band to blank. And in
Sure, so
fact,
that's really a mask. Okay.
yeah, it's a
You had a
mask, yeah.
plot in there for cumulative SNR, and does that show that that you could have reduced the length of your sampling period, by hours, because you were good enough halfway through?
Yes,
Cumulative
yeah,
SNR.
yeah, but I need to do the measurement and to collect the data. I can't dynamically look at the data that's
Yes,
flowing in
but
the
of course,
file.
but for next time, I'm thinking.
Well, I don't need to. I can do it, but what this one tells me is that in fact, I could have stopped I started off with a signal to noise ratio of 4.85. If I do this rolling average, this tells me that I could have stopped here and got a signal to noise ratio of about 5.9. And that is just 10 sections. Now each section is about, the total lot is 4 hours, 40 minutes. Each section is about 2.1, 2.2 minutes. So 10 sections is 20 minutes. So from 10 minutes in to what did I say 10 minutes. So from 5 minutes to 15 minutes, all I needed is just fold in that section and I'd have got a signal to noise ratio of 5.9. I think this
On that particular sample, but there is scintillation, so you might have been lucky. Yeah.
yeah. So
But 20 minutes is better than 4 hours. So yeah.
oh, it is, yeah. But even the best I've had, 4 hours 40 minutes is about the longest I've done. I usually do about 3 hours, and the best signal to noise ratio I've measured before I did this software was 7:1, and that was a lucky day. BO329 scintillates like mad. I do a dozen measurements, and I see of those 12 measurements, 4 or 5 I won't be able to find anything in, or I haven't been able to find anything in. What I need to do now, I've done this, I've only just finished this software. It's not quite finished actually. but if I go back to some of those early ones, maybe I'll find something. But generally, with my original software, folding all of the data, then my success rate was less than 50%, I'd say, because of scintillation. And you can see in this one, you know, there's a strong scintillation in this region here, a less strong here, and less strong here, and less strong here. If I move that down, this is this is folding just 8 sections, and the scintillation is much clearer here. You can see these sections that
Because it's a smaller window.
is a smaller window, but you can see that the scintillation is different. I wouldn't take much notice of these, but certainly these ones, that is a measure of scintillation. Don't forget, each one of these sections is 183 periods, 183 true pulsar pulses. So I'm kind of averaging in the scintillation. And what I'm seeing is the scintillation, I'm averaging the scintillation, and it shows that the scintillation is completely random. You know, you can, that things could disappear for quite a long time.
Just a comment, I think your presentation is very good, very interesting. And I think that what you've done is you've worked at this for a long time and begin to understand more and more minute details and improving your ability to make this work. And so once you really got it working, then as you increase your sensitivity, you can then really begin to do observations.
Yeah. Well, one of the reasons I looked at the low signal to noise ratio was that I mentioned about Andrea Dell'imagine's software. He really is the pioneer. He brought out the software very early, and with my three-band RTL system, I used his software for it, which pours the data into Presto. And that's when I realized that Presto, whilst it's good at finding new pulsars, it's not good at recognizing pulsars at a very low level. It's got RFI mitigation software in it as well. And it can also do searches, and it'll find RFI, and it'll tell you that that's a pulsar at the sort of levels that I'm looking at. It really needs a pulsar at least 10:1 signals that integrates to at least 10:1 for you to be confident that that you've detected something. So I was making a lot of measurements using Presto, and Giorgio Dell'Imagine, and Andrea's son, he produced me a bit of software, a bit of Python software, so I could look at the ones that Presto found to actually look at the signal to noise ratio and check that I've got a pulsar that way. But that was pretty time consuming as well, but it is possible. But I think that the reason for wanting to go to lower signal to noise ratios, I could have easily have built another couple of antennas and had a quad, and I'd have got my 10:1 signal to noise ratios and been quite happy. But I wanted to understand what the noise was doing and what RFI was doing, and what I could find out with the properties of pulsars, whether I could really recognize them at a low level. But this is applicable to people with big telescopes. Everybody with a big telescope all use variations of Andrea's software and Marcus's software, and followed by Presto. And they're really pleased when they can find, I can only find one pulsar, BO329. They can find with their 6 meter dishes or 7 meter dishes, they can find half a dozen pulsars. But even then, they've got to wait until they get a good day so that they can get their pulsar count up. If you can actually recognize a pulsar at a 4:1 signal to noise ratio with a big dish, there are more pulsars at lower level than there are at high level. So I think it would be useful for people with bigger dishes. I did talk to Professor Ransom, who developed the Presto software, and asked him why he didn't produce a signal to noise ratio. He uses the chi-square statistic to detect pulsars. Why he didn't use signal to noise ratio, and it's because signal to noise ratio needs a lot more computation and it slows up his software. But that's all I've done. I think I've copied what he's been doing in Presto and writing specific software for it, and it's been fun.
Yeah.
So a further comment about RFI, Peter, is that along with scintillation, you can probably get SNR variability just due to broadband noise fluctuations within the band, where there are no identifiable narrowband interferers, but the entire band can get broadband interference that kind of fluctuates over time during the course of your observation. And that will also drive variability in your SNR.
Yeah, it does. The noise does. You see, at 4:1 signal to noise ratio, you don't know. Like I've measured 5:1 here, but that means that the signal appears to be 5 times the size of the noise. But it could be a 4:1, and the noise is adding to it. You've got a noise spike adding to it to make it up to 5:1. So the technique I've been adopting is that when you, I don't think I've got the plot here. If you've got something like this, I haven't plotted the signal to noise ratio of all of the sections. So what I can say here is that the signal to noise ratio in band 0 is less than 0. So I might as well blank that band. So if I blanked that band, then this point would go up to here. And so and it would raise it up all the way along that. This point here, I could blank that. And you can see that is this, because it's a low signal to noise ratio, is pulling it down again. So I could blank that band, and that would leave it up at this sort of level. Now, if I do that with sections, I find that when I'm doing the sections, actually, I think the one that would be good for that is, like, this is telling me what the signal to noise ratio is in each of the sections. It's not telling me the signal to noise ratio because it's not in signal to noise ratio scale. But what I can do is I can blank that section, I could blank that section, I could blank that section and that section, and my signal to noise ratio would go up, and it does go up. But you don't know whether that is whether what you're doing is there a bit of signal in there, or is there a bit of noise that's pulling those up? You don't know. But what I do know is that I might be going a bit too popular here. That if I blank a band, now as you notice here that the bass noise is pulling that down there, so it's not quite peak. What I'd like to see that is to peak at 26.7, which is the proper DM of the dispersion measure of BO329. But if I blank any band and then I rerun this, if I find that that does in fact go up, then I know I'm getting rid of noise and not just, you know, making my signal to noise ratio better.
Right.
So the DM, getting a better DM, as this is getting a bit better than that. If I blank all of those negative bands and this gets better, then I know that's a valid thing to do. But I haven't done that. I haven't blanked any band for this. This is just raw. But that's the area that I'm getting into now.
Right.
Well, I've kept
Okay, thank you
everybody
very
a bit
much.
too long, haven't I?
No, this is great, Peter. Thank you very much. I really am glad that there's so many comments in your talk and everything. So thank you, everybody. And I hope that we can see everybody at the VLA next year in New Mexico in real life instead of just doing virtual conferences. I think virtual conferences have been quite an interesting experience for me, and certainly helped us keep together the organization in these difficult years we've experienced. But I'm looking forward to getting back to in-person conferences as soon as possible. So maybe next year we can actually do it that way. And I think maybe Rich has a few final words. For myself, I want to thank all of the speakers for contributing their talks, and especially Dr. Barron for agreeing to be our keynote speaker. And I think we were all very satisfied that this has been a great conference. So thank you all. Go ahead, Rich.
Yeah, on behalf of the board and the SARA officers, I want to thank David for setting up an outstanding conference. This is a lot of hard background work that you probably don't notice it. Also, Brian O'Rourke handled all the financing and make sure everybody got the links and everybody got their memberships, and a lot of work the treasurer did. And also the speakers and you participants for asking such outstanding questions and being involved in SARA. So thanks everybody, and David, great job, and it's back to you.
Okay, thank you all. I'm going to sign off now because I think dinner's ready, and I'll see you maybe at the Drake's Lounge or the summer conference, and hopefully in person next year. Thank you very much. Goodbye.